In 24.6, we're going to start out by looking at the expected value of a random variable. Then we'll look at variance and standard deviation of a random variable. Earlier in this chapter, in the last module, we were looking at sample mean, sample variance, and sample standard deviation. Now we're going to be talking about a population that's described by a PMF or a PDF, and looking at its means, variance, or standard deviation. The expectation or expected value, which we'll write as e of x, of a random variable x is often called the mean value of the random variable, which we would write as mu sub x. It represents an average value of the random variable, and it's not affected by variation about the mean. To calculate the expectation of a discrete random variable, that is, a variable that can only have whole numbers, the expected value is obtained using the equation that you see here. We sum over all possible values of x, the sum of the probability lump at that x times the value of x that x takes there. For the case we considered earlier of the roll of a die, you can't have a roll that comes out in 2.5. You can only have the whole numbers, and each one has equal probability of 1/6. So by applying this equation, each probability lump 1/6 would be multiplied by its value, so it's 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3, etc. And then when you get to the end, what you get there with that sum is the mean value. For the roll of a die, that comes out to be a mean value of 3.5. So as this points out, notice that the expected value does not have to coincide with one of the possible outcomes. 3.5 isn't a possibility when you roll a die, but it is the expected value that you would get, because half the values would be above it and half the values would be below it, or it's a symmetric distribution, so you should expect the mean to be right in the middle. For a continuous random variable, it's very different. The expected value of a continuous random variable isn't found by summation, it's found by integration. And what we integrate across the entire sample space, so the full range of all x's, from the smallest x to the largest x, we integrate x times f of x. There's a parallel between this equation and the last one that involves summation, but what we do here is integrate this slightly more complicated function than we were having to integrate to get the CDF. Note that if the PDF of a continuous random variable is symmetric about a particular point mu, then mu is the expected value. So if you happen to have a symmetric matrix, you can be assured that the midpoint, that mu, is the expected value. Thus, for this bell-shaped curve, the expected value would fall right on the axis of symmetry, and the value of mu would then be the mean value for this expected value. The equation will demonstrate that for you, but you can know it in advance if you can be assured of symmetry. The variance of a random variable measures the spread of the random variable about its mean value, and it can be found in one of two ways: either expected value of the quantity x minus the mean squared, or it can also be obtained as the expected value of x squared minus the mean squared. And I had already switched to calling e of x the mean in that expression. If you want to see the derivation of both of these, you can find that in your textbook. I'd like to point out that the second of these is usually the one most useful, and when you actually apply the equation, it turns out that we get that the variance of the variable x can be found by integrating across the entire sample space the quantity x squared times f of x, and once you've completed that integration, you just subtract the mean squared. That's the more straightforward way to find this. The standard deviation then would be the positive square root of the variance, the same as we found for a sample variance and sample standard deviation. I wanted to illustrate some of these issues. Here are two distributions with different means but identical variances. So you see the spread's the same in both curves, but one has a distinctly higher mean than the other. Here are two distributions that have identical mean but very different variances. That you have one that has that is much broader, much wider or larger variance. Notice also that the one that is narrower, that isn't as wide, has a higher peak. The reason that this is true is because the sum, or the total area under each of these curves, must be 1. So that means that the peak will have to be lower when you spread a distribution out wider. In 24.7, we look at the binomial distribution. The binomial distribution describes the results of a collection of n independent Bernoulli trials. Bernoulli trials is something that are individual outcomes that have a certain likelihood of occurrence of a certain likelihood of occurrence of making a long explanation of something as simple as a coin toss or the roll of a die. Something that could come out with what we're going to call the success or outcome of interest in with a certain probability p. With the head coin toss, the chance of getting ahead would be 0.5. And with the roll of a die, the chance of getting a 4 would be 1/6. P then would be our parameter of the probability of that particular outcome. In order to apply the binomial distribution, it's going to be telling us, for example, if we're interested in heads in a coin toss, it could tell us how many heads we might get in 6 tosses of the coin. You might toss the coin 6 times and get 0 heads, or 1, or 2, or 3, or 5, or 6. Can't have more heads than tosses. So in our case, x will be the number of heads that we get, and n would be the total number of coin tosses we're going to make, and the probability of getting ahead in any one toss is p, or 1/2. And this then is the equation that we'd use in order to find that. And notice that we need the binomial coefficient n upon x times p raised to the x times the quantity 1 minus p raised to the n minus x. The average value, or expected value, of this distribution is equal to n times p, and the variance is given by n times p times 1 minus p. The Poisson distribution is the other distribution we're going to consider in this section. It looks at a special case of the binomial distribution when n is going to infinity. In this case, we have a certain number of intervals in either time or space, and we're not talking about trials now. Some examples of applications where this comes up: to a geologist who's boring a new hole, you might look at the number of new beds encountered per foot of depth that as you drill. Or if you're working in a mine, you might look at the number of rock bursts in that mine per year. Or if you're a hydrologist, you might look at the number of floods that occur in a particular location each year, or per year, or per month. Some of the assumptions of the Poisson distribution are, first, that we have stationarity. What that means is that the probability of a single event occurring in a very short interval of time or space is approximately proportional to the length of that interval. So the probability of a flood in 1 month would be about 1/3 the probability of having a flood over a 3-month interval. Again, the probability of that event occurring is proportional to the length of the interval considered. Non-multiplicity. This assumption states that the probability of more than one event occurring in a very small interval is negligible. It would say that you can't have 2 floods at the same time, that you can only have one flood occurring at a time. Independence is another assumption, and it states that the number of incidents in any one interval is independent of the number in any other non-overlapping interval. So just because we had a flood last month doesn't mean the probability of a flood in the next month is in any way changed. That's not necessarily true in the case of floods. As you know, for example, if you've looked at the history of uh, flood levels along the Mississippi, is that we tend to have seasons. And so that it's questionable about whether or not the Poisson distribution would do a good job of predicting floods along the Mississippi. But in many applications, um, the this assumption is valid and the Poisson distribution is very useful. Traffic counts is another area where civil engineers often look at applying the Poisson distribution. The probability mass function for the Poisson distribution looks very different than we got for the binomial distribution. Here we need to calculate the probability of a certain number of occurrences x as e raised to the minus lambda, and lambda is the parameter of the distribution, multiplied by lambda raised to the x divided by x factorial. In general, the lambda is telling us the average number of occurrences per interval, and so that's the parameter that we use, and the mean and variance of this PMF happens to be very easy to calculate. It's equal to lambda. So that's a curiosity. Actually using the probability mass function will take just a few tries for you, but I think you'll find that it's one of the more straightforward applications. Here's the probability mass function for the Poisson distribution with a couple different values of lambda, and you can see that depending on the value of lambda, it can have a very different shape. There's actually a trick to simplifying Poisson distribution calculations that can be very handy if I ask what's the probability that you'll have 5 or fewer occurrences in this interval. Well, that means you have to calculate the probability that 0 happen, that 1 happens, that 2 happens, that 3 happens, that 4 happens, that 5 happen, and sum them all. That can get a bit tedious, and one of the ways that we can avoid that tedium is taking advantage of this trick. And I show an example here for a distribution where lambda is equal to 4.5. I'm showing how you can get the probability that 6 occur from the value that you get when you have 5. We first have the probability of getting exactly 5 from e to the minus 4.5 times 4.5 raised to the 5 divided by 5 factorial, and we get a certain probability in this case. To get the probability that 6 occur, we could reuse the same equation again, or you can just take the previous probability that 5 occur, multiply it by another lambda, and divide it by 6. So we can get the probability of 6 occurring from the probability of 5 occurring fairly easily. And this recursion formula is one that you might want to use for your problems and on an exam. We're skipping the hypergeometric distribution, so we won't be covering this in this section, and the only ones we're considering are the binomial distribution and the Poisson distribution from this section.